Welcome to my channel Lesson Physics. All of us use TV, mobile phones, computers, all of which are composed of basically a large number of diodes and transistors. Diodes and transistors are composed of semiconductors. So it is very much interesting to know how semiconductor diodes work. In intrinsic semiconductor, just like this, silicon or germanium have 4 valence electrons. 1, 2, 3, 4. Each atom forms covalent bond with 4 nearest neighboring atoms. These are the 4 nearest neighboring atoms of this atom, so they are forming covalent bonds, forming an octet. Each electron is shared by both the atoms, making an octet. So, valence electrons are not available for the conduction of electricity at 0 Kelvin. And crystal behaves as perfect insulator. But at room temperature, say 300 Kelvin, a few electrons acquire sufficient kinetic energy from the thermal agitation and break their covalent bond. The dislodge of negative electrons, can wander freely in a random fashion, leaving behind a vacant space called holes with positive charge. Thus, hole moving opposite to electron together with electron take part in conduction of electricity. Opposite to this bond cleavage, electron-hole pair generation, recombination of electron and holes makes free electron into a bond electron. Conduction of electricity in semiconductors can be increased significantly by doping, that is injecting impurity atoms to the intrinsic or pure semiconductor. These are called extrinsic semiconductor. When a trivalent element, there are 3 valence electrons here. Say aluminium is doped, that is injected in silicon. 3 outermost electrons of aluminium make covalent bond with 3 silicon atoms. This is the aluminium atom having 3 outermost electrons forming covalent bond with neighboring silicon atoms. But it lacks by 1 electron to form the 4th covalent bond with 4th neighbor. The vacancy that exists in the 4th bond constitute a hole. Corresponding to each doped arsenic atom, there is 1 hole. And the number is enormous, as because number of doping is enormous. Doping concentration is made very large. When an electron from neighboring atom comes to this position of the hole, fills the hole, a new hole is created at that neighboring atom. So, direction of flow of electron is opposite to the direction of flow of hole. Here is also creation of electron and hole pair due to this thermal bond cleavage at room temperature, giving rise to few electrons as minority carriers, and holes are here majority carriers. As here positive holes are majority carriers, the name is p-type semiconductor. Here minority carriers are electrons and majority carriers are holes. In n-type semiconductor, a pentavalent element, say arsenic, is doped. Here doping is pentavalent element. Silicon is replaced by a pentavalent element, say arsenic. When a pentavalent element like arsenic is doped into silicon, it replaces one of the silicon atoms and shares its 4 electrons with neighboring 4 silicon atoms, and 5th electron becomes almost free. The energy required to discharge this electron is only 0.05 electron volt. Almost all the arsenic atoms, impurity atoms, become positive ions, donating their 5th electron, and become, as it donates electron, negatively charged electron, it becomes positive. So they are positive donor atoms. In addition, there are free electron and holes due to thermal breakage of covalent bonds. Here electrons are majority carriers and holes are minority carriers, since holes are extinguished by recombination with large number of free electrons present in the n-type semiconductor. Suppose blue ball is the electron and the blue cone is the seat of the electron. Then right seat is vacant. Suppose this is a hole, lack of electron, so it is a positive hole. An electron sitting in this cone is negatively charged. When electron swims to the vacant seat at its right, as if vacant seat moves to the left, and as it is lack of negative charge, it is considered as positive holes. So as electron swims towards right, hole swims towards left. So the motion of electron is opposite to the motion of holes. But in any convention, the direction of current is opposite to the flow of direction of electron. So electron current is also in the left direction and current due to holes is also in the left direction in this figure. So total current is actual contribution from two components. One is due to hole, this is called hole current, and another is due to electrons, it is called electron current. So total current is I is equal to I hole plus I electron. I am repeating this as it is very important. As electron flows in this direction, the current due to electron is in the I electron is in this direction. Hole, as it is moved in the leftward, so it is I hole. The direction of I hole and the direction of I electron are same. It is towards left in this figure. So total current is I hole plus I electron is equal to total current I. This phenomena is very important in discussing the current components in semiconductor diodes as well as in transistors. So this is to be noted. In an unbiased PN junction, there exists an intrinsic potential barrier. What is this potential barrier? When it is unbiased, then concentration of electron in the N side is larger than the minority carriers in the right hand side. So electrons diffuses from left side to right side. Again, concentration of holes is much greater than the minority carriers holes in the N side. So holes are also moving in this direction. Diffusion takes place. At the junction, this is the junction of N side and P side. At the junction, when the electrons flows from N side to P side, it leaves a positive donor ion behind it. In a similar fashion, when a hole moves in this direction, it leaves behind a negative acceptor ions. So at the junction, when electron and hole recombines, giving rise to heat or light, if it is light, the kinetic energy is liberated in the form of light, then it is called light emitting diode. But in usual diodes, it is liberated in the form of heat. So kinetic energy is exhausted in the form of heat and they are neutralized here. So they are leaving behind positive charges at the left hand side in the N side and negative charges in the P side. So there is a potential gradient in this field, and this field is called potential barrier because these positive charges repulses further flow of these negative charges repulses the flow of electron, these positive charges repulses the flow of holes. So this region is depleted of any mobile charge. These donor positive ions, they are tightly bound to the silicon atoms. These negative acceptor ions also are bound to the silicon atoms. So they are bound. They are not free to move. So this region is depleted of mobile charges. Electron and holes recombine here. So it is left with positive donor ions at the left hand side in the N side and negative acceptor ions at the right hand side, that is in the P side. So this is positive, this is negative. A field acts in this direction. This field helps the flow of minority carriers but resists the flow of majority carriers. So a potential like this is formed. Here it is positive, this is positive. Here it is negative, this potential is negative. This is distance from the junction and it is the potential. Y-axis is potential, x-axis is distance from the junction. As we go far from the junction, it is more negative. So it is more negative, it is more positive, it is more positive. Actually, the value of this potential barrier is 0.7 volt for germanium and it is 1.1 electron volt for silicon. So actually unbiased PN junction does not carry any electricity, so it is a dynamic equilibrium because minority carriers flows from both sides, which is counterbalanced by the high speed electrons or high speed holes. Although they are very small in amount, they counterbalances the minority flows. So it is a dynamic equilibrium. Now, if we apply a battery, if we connect a battery in such a manner that positive terminal of the battery is connected to the P side and negative terminal is connected to the N side, this is called forward bias diode. This negative potential repels these electrons in this direction, and this positive potential attracts these electrons, whereas this positive terminal repels these holes in this direction and this negative terminal attracts these holes. So electrons are flowing in this direction, so current due to electron is in this direction. Similarly, current due to holes in this direction, so there is a current in this direction as a whole. This is forward biased PN junction. But this battery voltage must exceed the potential barrier, that is 0.7 volt for germanium and 1.1 volt for silicon. In the other hand, if we connect N side with the positive terminal of the battery and P side with the negative terminal of the battery, it is called reverse biased. In this case, potential barrier increases. This positive terminal attracts these electrons in this direction, and negative terminal attracts these holes in this direction, so potential barrier increases. The actual potential picture is like this. When it is forward biased, this is the potential barrier. This is the potential barrier VB voltage. When a forward bias V is applied, this potential barrier is decreased by an amount V, so the value is VB minus V. This is the forward bias condition. But in the negative reverse bias condition, the pink line, dotted line, indicates the increment of the potential barrier. VB was the previous potential barrier in the unbiased PN junction. But when it is reverse biased, then the potential barrier is increased by the amount V applied by the battery in the reverse direction. So now potential barrier increases, it increased to VB plus V. So I am repeating all these things in a nutshell form. In an unbiased PN junction, there exists an intrinsic potential barrier VB, which tends to oppose the movement of majority holes from P side to N side and that of majority electrons from N side to P side. Now, if an external voltage V is applied in such a way that P side becomes positive and N side becomes negative, then the intrinsic potential barrier VB is reduced by VB minus V. The junction is then said to be forward biased. Now a good number of holes from P side will be able to overcome this reduced potential barrier and diffuse into N side. Similarly, a good number of electrons from inside will be able to cross the reduced barrier and diffuse into P region. These two flows constitute a large current, I hole plus I electron is equal to I in the same direction. That is very important. Both currents are in the same direction. In the same direction. The current is in the same direction. Electron and then so same direction. This is very important. Total current is in the same direction. This is called forward current, which increases exponentially with the applied voltage. The minority carriers that is electron in the P side and holes in the N side flow down the potential barrier and constitute a small fraction of total current in opposite direction. This is called reverse saturation current. If the polarity of the applied voltage is reversed such that P side becomes negative and N side becomes positive, the height of intrinsic potential barriers is increased by Vb plus V. The junction is then said to be reverse biased. The increased barrier height makes the current due to flow of majority carriers negligible. Minority carriers move down the potential barrier and hence their motion is not affected by the barrier height. They constitute a small current in the reverse direction called reverse saturation current. Thus, a PN junction allows easy flow of charge in one direction but restrains the flow in the opposite direction. It indicates that PN junction can act as a rectifying element for the conversion of AC into DC. Thank you. Please watch the video and wait for my next video on transistor, which is totally function of transistor. The action of transistor can be explained with the help of action of diode. So this video is very much important for understanding the next video on transistor. Thanking you again.